Yeah. So I'm Sambrita, working with Ghatak. So today is a Monsoon Cafe, and we talk about the age-old problem that why are we still looking for MISO? I mean, MISO has been discovered in 1979 or 80. Our department has played a big role in that, but still there are a lot of debates regarding the mechanism. So I will try to show that there are some major loopholes in popular MISO hypothesis, and that is the reason why we are looking for the better mechanism. So Kalidasa said, Asharashya Prathama Divase, Meghmasishta Shanu, Garjanti Megha Parinata Gaja, Prekshaniyam Dadash. So in the first day of Ashar, the valley is covered with cloud, and it looks like adult elephants. So the question is, which calendar did Kalidasa use? So probably he is believed to be in the Vikramaditya's court. So it might be Vikram Sambat, but the Vikram Sambat came into being in historically many years after Vikramaditya. So it may be Shakabda. So I'm not sure about the conversion from the Gregorian calendar to that, but if we believe in today's Asharashya Prathama Divas, that's the first Ashar, that will be more or less like 15th June. And in this story, the Yaksha, who was banished from Kubera's court, is somewhere near central India, up a mountain called Ramagiri. So if we now look at today's southwest monsoon and the advance of that, so the normal date of monsoon, 15th June, that's the Asharashya Prathama Divas, and it's clearly goes through the central India. So probably even Kalidasa knew that's something, the onset of monsoon over the central India. And interestingly, later in the Meghaduta, the Kalidasa said that ultimately the Yaksha told the cloud to deliver his message to his beloved, who is in Alkapuri, Himalayas. So clearly there is some idea that something is going north. The cloud is going north from central India to the foothills of Himalaya. And probably it's the initial thing, that's the initial progress of monsoon, not the MISO kind of thing. But we have our papers like Nirupam showed with Booz and others that it is somewhat connected to MISO, the first MISO progression. Now, this is 1979 when first from observation, from satellite data, people saw something moving north. So it's 72 to 84 degrees east, and they are plotting cloudiness, and clearly something is coming below equator and it's moving up to 30 degrees or so, the cloudiness pattern. So first we have already identified that something is moving north. I think independently in our department also, Professor Gadgil, probably she is online, so it's a great fortune. So they also showed that 1977 to 1973, in 5 years, they have clearly again seen from the MCZ, that is the maximum cloudiness zone, they have seen it moving north, clearly moving north. So we are talking about the convection that moves north, and it's kind of wave kind of pattern. So I think most of the people here are very much know about this, but still. Now always in Monsoon Cafe there will be 1 or 2 slides that clouds doesn't only move north, but also a prized fish, prized catch. That's called hilsa. And it's famous for Bangladesh and West Bengal side, but clearly in the Godavari region also they are estuarine fish, but for spawning they went into the freshwater. And interestingly, I found one interesting news that initially the hilsa used to move through Ganges and go up to Allahabad and Patna. But for the Farakka beach, Farakka Barrage, Now they cannot move past Farakka, and some point in time they have opened the gate for 4 hours to let the Hilsa pass to Bihar and UP. Yeah. So and the another place where the Hilsa is also very important culturally is the Sindh. Again for the barrage over Indus. Now nowadays the catch is very low, but in Sindh it's called Palla. And this is the football club East Bengal that became synonymous with Hilsa. And this is three types. The Godavari Hilsa is called Hilsa. This is the Bengal Hilsa with mustard, and this is the Palla. And in popular culture, it's very important that because in Sindh, the most important god, the Jhulelal, his mount is Hilsa. Now coming back to convection. So the northward propagating convection, Lawrence and Webster in 2002, they have made a composite which clearly shows the structure of this northward propagating convective movement. So it starts from day minus lag day minus 4 up to day 16. So we see first something coming over central, equatorial Indian Ocean. Then it moves up. Then some part goes into the Arabian Sea, and at like 8 day, we now see that something also moving east. At 12, it almost covers the whole North India, Northern Indian region, and yeah, and 16 we see the next dry lobe is coming, and also the movement here, the sign has clearly changed. So there is a movement in Western Pacific also, Western North Pacific. So this thing is called the BSISO, in contrast to MJO, because in boreal summer, the structure of the waves in 50 interseasonal oscillation in 30 to 60 or 25 to 80 or 20 to 90, whatever, this region of frequency, we clearly see this movement, and it particularly influences the South Asian monsoon and Southeast Asian monsoon. So it influence over the monsoon onset, monsoon active break cycle, and low pressure system and all is very, very clear. So it's very important to understand the mechanism why it moves north. So the theories of BSISO, when it came into being, came into knowledge in around 1980. From then on, a lot of studies have been done. So in the old days, when there was no reanalysis, good reanalysis data, the studies like Webster in 1983 or India et al. Or Visa 1992, I guess Professor Jace was also there. So these studies took the axisymmetric model, and in these things like the interaction or land was important. Webster talking about the surface hydrology and all. But with time, in modern time, near 2000 or so, the theories came into being, and mostly the popular theories that is in place today, we can categorize it in three broad categories. That is the coupling between background shear and convection generated circulation. The other is moisture attraction or the moisture mode framework that I will talk about later. And the third is air's interaction, though its influence is somewhat low. That's more or less people now agree, but still there is a lot of theories about the air's interaction. So this is what the most important paper in the first group of theories, and the mechanism it's Xiang et al. 2004. So Xiang, it's in Binwang's group in Hawaii. So Professor Xiang, Tim Lee, and Binwang, they came up with the understanding how we think it's totally atmospheric internal dynamics, how this convection can move northward. So their idea is initially there is some baroclinic divergence associated with the convection that starts over the Indian Ocean region, and there is a gradient of that. The gradient is meridional gradient, and we know in the monsoon there is a clear monsoon background wind. There is a clear climatological monsoon wind. There is a clear shear, vertical easterly shear. and when these two cooperates with each other in their simpler theory, they have found a connection that then this vorticity, positive vorticity gets generated north of the convection, and but in the free troposphere. And for the free troposphere positive vorticity generation, using their equation, they have shown there will be divergence, there will be some conversion, there will be convergence in the boundary layer, and boundary layer is moist, and the moist convergence will take place, and the convection will move north. So more or less that's the theory. So what in this theory, the take home message is the most important thing here is the vertical easterly shear, and the way the vertical easterly shear moves the northward propagation is due to the convergence that is happening because of the internal dynamics, the convergence in the planetary boundary layer. This will kick in convection. That's the theory. So Vishal Dixit and Professor J.S. they modified the Young's theory, I guess 2011. There are many papers in this line. So this is one of the interesting paper where they claim that not only the meridional shear of the vertical shear of the zonal wind, but also the vertical shear of the meridional wind influences the northern propagation, and the mechanism they showed is also like the generation of positive vorticity. They showed that there will be a generation of barotropic divergence itself because of this this shear of meridional wind. And again, the essential dynamics is more or less similar, that there will be a convergence in the planetary boundary layer, and from the convergence there will be moisture convergence, and this will ultimately leads to northward propagation. Now the moisture convergence is a quantifiable quantity. So now we can, with reanalysis data, we can check. This is another paper, Bellon and Sobel. Again, they say that meridional advection of vorticity by the mean flow is responsible for the creation of free tropospheric vorticity. Somewhat different kind of generation of vorticity, but again, the vorticity in turn creates boundary layer convergence where Coriolis acceleration and subsequent northward movement. So again, these things is boiling down to the boundary layer moisture convergence. So these all the theories in this slide, they are ultimately boiling down to boundary layer moisture convergence. So now I am coming to one of our work. Here we used NOAA Whaler and ERA 5 data. We have taken 25 years, 1985 to 2009, and the filtering is just like Lawrence and Webster, 15 to 80. So now if we carefully look at, so this is Whaler and this is column integrated specific humidity, and this is scaled by L, because if people want to compare with MSC, it will be easier. So one can clearly see, say at day minus 12. So at day minus 12, we can clearly see this Whaler, the higher than average anomalous Whaler. That signifies the subsidence of the dry gas is clearly co-located with the column integrated specific humidity, which is below average. It's clearly co-located from the shape. Next day again we can see. Just let's take day 0. Again we can see. So more or less we can say that the column integrated specific humidity is very much co-located with the Whaler or convection or maybe rainfall. Also, Whaler is a proxy of rainfall. So from these observations and the weak temperature gradient approximation that came being via Sobel and others, the new theories came into being, which is called moisture mode. So essentially, moisture mode says that this kind of ISOs is basically dominated by, clearly dominated by and dictated by the column integrated specific humidity in the free troposphere. So we can see that column integrated specific humidity is clearly co-located. So if we can try to understand the dynamics of the column integrated specific humidity, how it evolves with time and space, then hopefully we can understand the structure of the BSISO. So that's the whole idea. Yeah, and now I just want to just focus on few things. That first we see the convection is coming over Indian Ocean, then it is becoming bigger. Now it clearly moves towards Arabian Sea first, not big. Now it first moves in the Arabian Sea, then it gets a clear tilted structure, and then the whole thing moves up, and by day 12 and day 16 it covers whole northern India, and now it moves also in the big, and the next cycle comes. That's the way it evolves. Now to understand the moisture scenario, the column integrated specific how it evolves, we will appeal to the moisture budget equation. So here are two equations. I am just briefly describing because we will need it later. So this is the specific humidity or the moisture, you can say. That's, and this bracket is for the column integration. So it's the column integrated specific humidity. This is the horizontal advection. This is vertical advection. This is precipitation. This is evaporation, and this is the residual in the bucket. So these four terms will happen in a column. So vertical advection will happen vertically, and precipitation, evaporation, and this thing. So all of these things we can call these four terms together. We can call it column process. And now, as I told that I will try to look at the moisture convergence thing, that is describe the first class of theories, Ziang and others. So this vertical advection term can be decomposed into two terms. One is the horizontal moisture convergence, and these can be called the vertical convergence of moisture flux. So this term will be ultimately important because anyway the class of theories that talk about the vertical shear and its coupling with the convection, they will ultimately talk the main reason behind the non-flux propagation is this term, which will ultimately come in this term. So first, slight detour to understand this. Okay, slight detour to understand this. I will start from MGO, the other kind of ISO that is most prevalent during winter. So this is taken from Su and Lee. So again, the Lee was in the Xiang paper, old Xiang Lee one. So here is this is the MGO. This is the MGO moisture, MGO filtered specific humidity. Yes, this is the MGO filtered specific humidity, and we clearly see that it's 40 east to 180 west. So towards east, MGO is highly tilted, and the moisture tendency that will ultimately move these things towards east is also tilted. So the whole structure will be tilted. From this, in this way, they assume that something will first happen in the planetary boundary layer because the tilted structure. If you look at this place, there will be not much humidity here. Most of the moisture is in up to 500 hectopascal. So first it will come near surface in planetary boundary layer, and then it will move up, and this thing will move here. So that's the whole idea. So my point of showing the this MGO is the idea of the moisture convergence and the old, the Xiang's class of theories that has no quarrel with the moisture mode idea. So this work is clear. These two both of this work is clearly done by the moisture mode idea, but clearly the moisture convergence in the planetary boundary layer is very important in case of MGO. The way Xiang thought it will be important in BSISO. So here you can see this is the Q2 by L is basically the moisture sink or source, that is the precipitation and evaporation, both direct residual, and this is the vertical advection. So this together will ultimately, again, when you see partial T, that's the moisture tendency. Again, we will see the eastward tilted structure, and first something comes over this planetary boundary. So when we look at it, clearly this term, that's the advection. The advection term helps in moistening somewhere near the free troposphere, not in the boundary layer, but in the boundary layer and above. is basically coming from this so-called column process. The 4 terms I have mentioned. So it's basically coming from those things, and in the most strong influence of the column process will ultimately come from this vertical advection. Now I will try to show the decomposition of the vertical advection. So this is vertical advection, and this is the other moisture source and sea. When we add these two up, we'll basically get this structure. So here it is green. Here it is green. So it's essentially dictated by this term. This term is winning over this. So now if we decompose this term, we clearly see this is the moisture convergence and this is the other term. So moisture convergence is clearly preceding the convection first, and in the boundary layer we see a huge moisture convergence associated with the MJO circulation. And the other term is also important, but that's above boundary layer. So when we add the last two terms, we get back this. But my point is, near the planetary boundary layer, it is indeed the Weysian thought. In case of MGO, it's indeed the moisture convergence that is giving the moisturing in the planetary boundary layer first. And this time and after that, it will move up because of in the and your free troposphere, it will ultimately come from the horizontal advection. So horizontal advection is not the only important thing here. The moisture convergence is highly important in case of movement of MJ. Now again, coming back to fluently, because I just want to show another vertical structure of it, I'll just focus on these two. Clearly, there is some moisture convergence because in front, this is the convection center. In front of that, there is some convergence will happen because clearly if there is convergence, there will be some omega, upward omega. So we see the omega is clearly tilted, and the divergence plot again. This is the center of convection, but it is clearly tilted. So the convergence first happens below, and the omega structure also reflects that. So this is the schematic they used. So for MJO, they said there is some Kelvin wave above the planetary boundary layer, and for that there will be some convergence first in the planetary boundary layer, and that is why the convergence and the moisture convergence and everything that I have shown, the moisture first happen in this region, then it will move up due to advection. Now let us look at what happens in case of BSISO. So again, this is the old plot of specific humidity, column integrated specific humidity. Here I will just show that from day -8 to day -4, first these things move towards Arabian Sea, and next it moves deeply over Arabian Sea. So here I tried first to understand what happens over this region, why this thing is moving north. Is it the moisture convergence in the boundary layer? The Weysian thought. Now this is my tendency terms. Clearly you see the moisture tendency at day -8 is over Arabian Sea, very strong. But it clearly comes from horizontal advection. Column process is basically not helping it at all. But horizontal convection is winning anyway. That is why you are getting resultant moisturing here. And this is the precipitation, and this is the 3 components of column process that constitutes column process. This is the vertical advection, in which the moisture convergence is included, and we clearly see that is happening over equatorial Indian Ocean, but not over Arabian Sea. So essentially, what is happening over Arabian Sea, the whole northern formation is clearly dictated by horizontal advection, but not the vertical advection. Now, look at this vertical structure plots. So this is again at day -8, and I have focused on Arabian Sea, 60 to 72.5. So clearly we have seen the moisture structure that is not tilted towards north. It's clearly upright. Here moisture tendency also more or less upright. And when we talk about the budget terms, we clearly see that this column process and this is the horizontal advection, 2 component of budget term. And the column process is basically not helping the cause for moisture tendency, but it's clearly coming from horizontal advection. Now I have decomposed column process in horizontal moisture convergence and vertical convergence of moisture flux, the other term, to understand why whether Xiang's idea is working here or not. Clearly, where the moisture tendency is highest, here 10 to 20 degree, near 850 to 600 or so, clearly we see there is no moisture convergence here, but it's negative. Clearly it's negative here. So the idea of the moisture convergence in the planetary boundary layer in front of convection is not at all true. Even if it happens and if it helps it's basically coming above 700, a small part of coming from that, but that is essentially cut off by the this term. And ultimately, when we add these two, we'll get the vertical advection term, which is ultimately dominating the column process. So anyway, we see ultimately vertical advection is not helping at all the moisture conversion, the moisture tendency. The moisture tendency is totally dictated by horizontal advection. And I want to focus on the divergence and omega structure also. Omega structure is clearly applied. Just here for the MGO, the omega is tilted. So there in front of convection, there is some omega in the planetary boundary layer, but the omega is upright. This is for day -4, another day for consistency. Again, we see the moisture tendency is clearly coming from horizontal advection, not the column process. And there is some influence of moisture convergence that does not at all in the planetary boundary layer. If something happens that's happening over that, and when we just add these two up, we are ultimately getting a negative sign. So ultimately, horizontal advection is mostly dominating the moisture tendency here. The story is same. Omega is upright. Divergence is also upright. Just for comparing, I just again repeated that we must remember that for the MGO case, there is some planetary boundary layer moisture convergence, but in this case there is nothing. It's highly negative. It's actually not helping. And again, this is S. Ovik et al. So they have done the similar kind of structure, vertical structure. Again, they got vertical velocity which is quite upright. And vorticity again quite upright. In Xiang's theory, there is some vorticity will get generated over the free troposphere. So this should be tilted in this direction, and the vertical velocity should be tilted in this direction, as we have seen in this case, the divergence and vertical velocity, because there is some omega over the planetary boundary layer. But here there is nothing. It's clearly upright structure. And I think even Xiang also have not found that in his reanalysis studies, his vertical velocity is upright and specific humidity is upright. So his idea was a bit far-fetched, I think, to prove his theory right. Now, last time coming to the ARC interaction part. So, Professor Sambrita in 2001, I think Goswami was also there. They have shown that there is a coherent movement of OLR and SST. We clearly see there is a coherence, and this clear observation ultimately leads to the assumption that might be ARC interaction might help in outward propagation. And there are many modeling studies and all which talks about the ARC interaction. Now there is another plot from Sambrita sir's paper where they are showing when the north bay is clear. I guess this is black and white, so a bit difficult, but I think the SST is positive. So when there is strong convection over Indian Ocean, the convection is just getting started, and the north bay is clear. We see positive SST over this region, both Arabian Sea and Bay of Bengal. So from this one may think that wishy kind of thing might happen. So this is the bay is warm, the Arabian Sea is warm, so might be evaporation can help the build up of moisture. So that's one idea people can have. That I'm just coming back to again the tendency moisture budget plots, and see we are showing that evaporation is actually negative. So why evaporation negative? Though SST is warmer than normal, the SST anomaly is positive because we have clear monsoon wind which is coming from west, and the BSISO wind that precedes the convection is easterly. So it actually weakening the monsoon wind. So overall the wind is weakening. That is why the evaporation is also weaker. So that is why the evaporation is strong here. And probably I think as there is some strong horizontal attraction over here for the radiation thing, probably the SST is warmer, but it directly has no influence in build-up of moisture. The other way SST can influence moisture is probably the Linds and Bingham style, but again that style ultimately it has to come from the moisture convergence, and I have already discussed that moisture convergence is not very important here. If we just accept the moisture mode, that the moisture build-up, the column integrated moisture build-up is dictating the BSISO. So the last kind of theory, the most recent theory that has came, it talks about the moisture mode and it talks about the importance of advection. The way I have shown, the advection is important over here, so advection is dominating it. Here also, we can clearly see the tendency is dominated by advection, and how this advection is coming into being. They are saying in the climatology. This is the climatological moisture distribution. So there is a clear gradient towards west, and the easterly wind is actually taking the help of this distribution of specific humidity or moisture and keep moisturing the Arabian Sea, and that is why the horizontal advection is dominating the tendency here. But I want to just say that here the tendency is over Arabian Sea and not much over North India. They are saying is cutoff at 25. So, but this is not the first time this idea came into being. In 2016, again someone from our department, Joy Montero, was involved in this paper, Adams et al., and they have shown that the seasonality matters, and the MJO and the idea is MJO and BSISO is basically tying up the MJO and BSISO in one unified moisture mode idea, and they say that this is the moisture gradient, and again the western easterly wind ultimately helps it to move to moisture the Arabian Sea region. I won't say that this theory has a problem, but this theory I'd say is incomplete because here we can see I just mentioned that over 20 degrees there is not much moisturing, but when we look at the plots, the moisture plots, specific humidity plots, clearly we see that it doesn't stop here at 20 degrees. It moves over northern India and moves up to almost 30 degrees. So how this region of northern India and Pakistan is getting moisture, that is one idea. That is one clear question that the moisture mode paper still yet have not answered. And another interesting thing is when it starts, we see Rossby kind of gyre here, and this gyre is ultimately getting a very tilted shape towards, south, north, east, northwest to southeast tilted shape, this gyre over Arabian Sea. So why this gyre is moving in that way? Why the gyre got tilted in just 4 days or maybe 8 days? That is all. That question is also not answered by the moisture mode idea still yet. So that is the loopholes of the moisture mode idea that came into being in recent times. Yeah. So most of my thing is done. I will just end with one observation that this is yesterday's cumulative rainfall, and probably the in homogeneous region I will say the more or less India are not normal, but I will say that the homogeneous region of east and northeast is below normal, but though it's highly below normal, southern Bengal, Bihar, UP, this region, but over the northern Bengal and Assam, it's basically highly above normal, and few places are really flooding. So I have seen it many times that when this thing happens, there is a dipole kind of structure here. I don't know why, but when we take the whole region, the story will not come into being. But actually, I have seen this kind of pattern many times. 2019 was a clear case. That's it.
I'm just curious, you're using green article, right?
Sorry?
Using ERA, all this.
ERA, right.
So what is residue in your moisture?
This time residue is really small.
Huh?
Really small. There is not much residue.
They're not contributing to it because there is a lot of noise.
Yeah, so I did most of similar thing I have shown using NK-Penkar last year, and you made a comment about the moisture. That really helped because I have checked that over the Himalayan region, NK-Penkar moisture is very bad. So now I have.
What is it? 5%, 10%? What is it like?
Yeah, it not more than 10%. Yeah, and the Himalayan region I have checked. The NK-Penkar has highest moisture over the Himalayan region. That's clearly wrong, but ERA 5 doesn't have that problem.
Okay.
Yeah.
Just one question.
Yeah.
I mean, very nice presentation.
Sorry?
It's a very nice presentation.
Okay.
And you talked about various mechanisms of propagation.
Yeah.
Recently, I mean, you talked about 2016 with Joy.
Yeah.
And so with Joy. There's a recent paper, I think it's by Wang and
Sobel,
which gives you a unified theory. He takes it beyond the 2016 one, where he says that the same one explains both NGO and loss of propagation.
Yeah, so there is one paper called Unified Moisture Mode Framework. That's the paper I have just shown. This is Young et al. 2018, and there is the theory part where they use shallow water equation and all.
Yeah, 2021.
Yeah, that's called the moisture mode theory. Yeah.
That's a unified.
Yeah, there is a try of unifying these two things. Yeah.
Thank you.
Oh, just one thing. I just want to show. I just forgot there was a video. This was made by Shubhranshu, who joined just last year.
Okay.
So 2000, he had shown from May onwards, and the OLR propagation is very nicely shown here. The northward thing, the first one.
It's 2000, not
2000.
Okay.
Yeah. So I have found at least 2-3 very strong cases there. So I have taken this year.